How do the forces on your body depend on your position in the train? At least once, all of us went to roller coaster, and at least once, all of us asked ourselves how they work. A vertical loop is the most basic of roller coaster inversions. The train moves essentially in a vertical plane, upwards, over the top and down again, completing a 360 degrees of rotation. At the top, the rider is upside down. Modern roller coaster loops are not circles. Euler spirals and other mathematical curves have been introduced to obtain a smaller radius of curvature at the top and to avoid the sudden onset on a large forces on the rider. A photo of the vertical loop in the Cannone roller coaster at Leisenberg, where the front of the train of length L has just reacted at the top at T. Also shown is an approximating circle with the origin at O and radius R, and the angle alpha relating the train length L to the radius, and the formula is L equal to 2R alpha. The angle theta is introduced to describe the location of the middle of the train in relation to the highest point. The drawings represent the situation in the photo and also a later time when the train has passed the highest point and is moving with increasing speed at angular velocity. G marks the approximate location of the center of mass of the train. The graphic shows the measuring of the time t needed for the train to move over the top. An estimate of the speed can be obtained if the train length L is known or measured. Experimental and theoretical data for the total force on the rider from the train passing the loop. What about the acceleration? In this picture, we have a simplification of a three-axis acceleration coordinate system. The coordinate axes in the figure are commonly referred to as vertical z, longitudinal x, and lateral y, and rotate together with the rider. An example of analysis of vertical z acceleration versus time diagram for a ride close to the back in the roller coaster helix. The thin horizontal lines represents maximum allowed duration, whereas the thicker horizontal lines represent actual exposure at the level. The solid sloping lines represent average acceleration during the event. After the middle of the train has passed the top, the tangential component of gravity causes an increase of train speed, and it is shown in this diagram. The tangential acceleration of the train can be obtained by considering the time derivative of the angular momentum. L is equal to m multiplied for r multiplied for v, where m is the mass of the train. Since all parts of the train are moving along the circle orthogonal to the radius, the magnitude of the angular momentum can simply be written as L is equal to m multiplied for theta multiplied for r elevated by 2. This is three body diagrams of the forces on a rider in the front, middle and back of a roller coaster train. The picture to the left shows the situation where the front of the train is just reaching all the top. The picture to the right shows the middle of the train at the highest point. Single arrows mark forces with gravity always downwards. The acceleration is marked with lines with double arrows, and the tangential and normal components of the acceleration are indicated with dashed lines. These are the position of the front, middle and back of the train with marks at equal time intervals. The corresponding position for the front and back were obtained by adding or subtracting the angle alpha, that is equal to L divided for 2R. The sequence of dots finished at the same time, but at different position in the train for the three graphs, for comparison with the results from the frame-by-frame analysis shown in figure. A photo of a roller coaster loop combined with a knowledge of the length of the train, offers many possibilities for investigations of forces even before riding. The mass of the train is not needed for the equations of motion in the loop, as long as energy losses are neglected. The analysis of forces on a rider shows that wirelessness can only be obtained in the middle of the train. Using roller coasters and other amusement rides in physics, teaching brings an enjoyable connection between the experiences of your own body, Newton's laws and motion in 2 and 3 dimensions, and contributes to understand the vector character of force, velocity and acceleration. It is a common everyday experience. Nevertheless, designers of roller coaster rides limit this to improve the passenger comfort of the rides. Roller coaster passengers need time to sense acceleration changes. Even when human safety is not a physical issue and engineers expend considerable design effort, optimizing jerk and eliminating snap with the roller coaster rides to reduce maintenance and expand the life of the ride.